Hello. I'm just setting up my chat and then I will change to full screen. I'll continue with studying vectors like I did last stream. But I downloaded the PDF, so I'm going to be using that instead of learning it from the website. Because learning it from the website is like really slow. The last stream, I learned about vector notation. I'm going to be using that. It was about the dot product and cross product, learning it from the website. Wait, let me just change because learning it from the website is like really slow. The last stream, I learned about vector notation. I'm going to be using that. It was about the dot product and cross product, learning it from the website. Wait, let me just change because learning it from the website is like really slow. The last stream, I learned about vector notation. I'm going to be using that. It was about the dot product and cross product, learning it from the website. Hold on, the loading is taking a lot of time. The last stream, I learned about vector notation. I'm going to be using that. It was about the dot product and cross product, learning it from the website. Hold on, the loading is taking a lot of time. The last stream, I learned about Hold on, the loading is taking a lot of time. Hold on, the loading is taking a lot of time. Okay, let me just change to full screen. So I downloaded the PDF of Calculus Volume 3. And yeah, so this part was what I was studying last time, vectors in space. I did dot product and cross product. I will study this and maybe this chapter as well. Okay, I went to the previous chapter. Let me just go to the previous chapter. Okay, yeah, I remember learning about torque. Okay, equations of lines and planes in space. Should I make it a little bit bigger? Okay, I think this is fine. Equation for a line in space. Let's first explore what it means for two vectors to be parallel. Recall that parallel vectors must have the same or opposite directions. If two non-zero vectors u and v are parallel, we claim there must be a scalar k such that u is equal to kv. If these two are parallel, okay, the position of the vector doesn't matter, right? If u and v have the same direction, simply choose k which is the ratio between their magnitude. If u and v have opposite direction, choose k, which is the minus ratio between their magnitude. Note that the converse holds as well. If u is equal to kv for some scalar k, then either u or v have the same direction or opposite direction. So u and v are parallel. Therefore, two non-zero vectors u and v are parallel if and only if u is equal to kv. As in two dimensions, we can describe a line in space using a point on the line and a direction of the line or a parallel vector which we call the direction vector. Let L be a line in space passing through point P. So x0, y0 and z0. So P is over here. Let V, ABC be a vector parallel to L. Okay. Then for any point Q on line L, we know that PQ is parallel to V. Thus, as we discussed, there is a scalar t such that pq is equal to tv, which gives, okay. Using the vector operations, we can rewrite equation 2.11, which is this, as this. So xyz, a random point xyz is point P, plus it with some scalar t times the vector. So point P plus the vector v scaled or shrinked, and it can give any point on the line. So setting r as xyz and r0 as x0, y0, and z0, we have the vector equation of a line. So r is r0 plus tv. So t is a variable and r0 is fixed, right? And I'm guessing v is also fixed. Equating components. Equation 2.11 shows that the following equations are simultaneously true. So x minus x0 is equal to ta, y minus y0 is equal to tb, and z minus z0 is equal to tc. If we solve each of these equations for the component variables x, y, z, we get a set of equations in which each variable is defined in terms of the parameter t that together describe the line. This set of three equations form a set of parametric equation of a line. So x is equal to x0 plus ta, y is equal to y0 plus tb, and z is equal to z0 plus tc. If we solve for each of the equations for t, assuming a, b, c are non-zero, we get a different description of the same line. Because each expression equals t, they have the same value. We can set them equal to each other to create a symmetric line, symmetric equations of a line. So parametric and symmetric equations of a line. A line L parallel to vector v and passing through point P can be described by the following parametric equation. If the constants a, b, and c are all non-zero, then L can be described by the symmetric equation of the line. If you're doing the PDF, they show the solution right away. Find the parametric and symmetric equation of the line passing through point 1, 4, minus 2. I guess let's just do it anyways. Okay, so we have 1, 4, minus 2, minus 3, 5, and 0. Let's choose, wait, P as 1, 4, minus 2, whoops, and then Q as minus 3, 5, 0. So we have P and Q. So I can define vector V as, I can take Q minus P. So minus 3. Actually, let's do P minus Q. So 1 minus minus 3 would be 4. 4 minus 5 would be minus 1. Minus 2 minus 0 would be minus 2. So I guess we can say x, y, z is the point P plus like that, I think. I'm not really sure. Let's say t is negative 1. Then we have 1 minus 4, 4 minus minus 1, and minus 2 minus minus 2, which is 0. Okay. I guess this makes sense. Find the parametric and symmetric equation of the line passing through points this and this. So t is equal to -1. And then we have and then what? So I have to write it like this, right? So x is 1 plus, minus 4. So 1 minus 4. Is that correct? Hold on, let me just see the solution. 1 minus 4t. Then I think 4t. Then y is equal to 4 minus t. Then z, let's just put z here. Z is equal to minus 2 minus 2t. Let's see. But I think they must have done q minus p instead of p minus q. And then the symmetric one is x minus x0 divided by a. So 1 plus 4t divided by 4, right? So this divided by 4 should be equal to this divided by -1. Should be equal to this. Divided by this. Hold on, no, actually. No, I'm wrong. We're equating the t, right? So when they say ABC, what do they mean? They mean vector v. So this is ABC. This is x0, y0, z0. Okay. So x minus x0. I'll just write it here. So x0, y0, c0 plus it with t, a, b, c. C0 plus, okay, this makes sense. Okay. And then they say x minus x0 over a, and then y guess I can do 4 minus y. We are making t the subject, right? So z plus 2 divided by -2. Yeah, if I multiply by -1, I get that equation. Sometimes we don't want the equation of the whole line, just a line segment. In this case, we limit the values of our parameter t. For example, let P, which is this, and Q be points on a line, and let P and Q be the associated position vectors. In addition, let R be XYZ. We want to find a vector equation for the line segment between P and Q, using P as our known point on the line and PQ as this, as our direction vector equation gives this. So we have R is equal to P plus T PQ, and then we end up with this. Thus, the vector equation for a line passing through P and Q is R is equal to 1 minus TP plus TQ. Remember, we didn't want the equation of the whole line, just a line segment between P and Q. Hold on. Find the parametric equation of the line segment between points P and Q. So this is example 2.46. Find parametric equation between the points P and Q. So P is 214. Hold on. No, a point is not defined like this. Point is defined like this because the other bracket is a vector. 3 and -1 and 3. So the vector going from P to Q is so Q minus P, right? Yeah. 3 minus 2 is 1. Minus 1 minus 1 is -2. Then 3 minus 4 is -1. So we have R, which is any point on the line segment. This is XYZ, plus it with vector P. No, I mean equal to vector P plus T PQ. So 214 plus it with T1 minus 1. So what are we trying to find? So they got this. You're finding the parametric equation. X, Y, Z is 2 plus T, 1 minus 2T, and then 4 minus T. So that means we make T the subject of each equation. You have 2 minus 2 is equal to t, y minus 1 over negative 2, which is t, and then z minus 4 over negative 1, which is t. So basically, the z looks like a 2. Uh, let's see if this is right. Z is 4 minus t. Oh, they just wanted this. So x is 2 plus t. Y is 1 minus 2t, and then z is 4 minus t. But they wanted this also. So yeah, if we put the value of any value of q over here, for example 3, but here we get t is 1. So 1 is the max value of t, because we are only considering the equation for a line segment between p and q. So t can't be greater than 1. Distance between a point and a line. We already know how to calculate the distance between 2 points in space. We now expand this definition to describe the distance between a point and a line in space. Several real-world contexts exist when it is important to be able to calculate these distances. Let L be a line in the plane and M be any point not on the line. We have M, then we have line L. We are trying to find the distance t between the shortest distance t between M and the line L. We define the distance t from M to L as the length of the line segment MP, where P is a point on L such that MP is perpendicular to L. When we are looking for the distance between a line and a point in space, figure 2.64 still applies. We still define the distance as the length of the perpendicular line segment connecting the point to the line. In space, however, there is no clear way to know which point on the line creates a perpendicular line segment. Okay, anyways, the area for parallelogram vectors PM, so P, so this is the shortest distance. P is a little bit ahead. So area for parallelogram PM and V form the two sides of the parallelogram with the area of this. Using the formula from geometry, the area of this parallelogram can be calculated as a product of its base and height. So V times T. We can use this formula to find the general formula for the distance between a line in space and any point not on the line. So the D is basically the height of the parallelogram. Also, I forgot how you do cross product. Find the distance between T and point M 13113 and the line x minus 3. Wait, hold on. So we have example 2.47. So we have M as a point 113, and then we have the line L. So y plus 1 over 2, and then z is minus 3. So if we select a random point, wait, let me think about how we can do this. Is P and V selected randomly? Hold on. When you're defining the line this way, A, B, C and on the bottom, right? So we select V as that. I looked at the answer, by the way. So 4, 2 and 1. Wait, I think it's better if I 4D. So we have like that. Then y is equal to minus 1 plus 2t. I think it's easier if I imagine it like this. 3 plus t. So we have x, y, z is equal to a point minus 3, minus 1 and 3 plus t 4, 2, 1. This is the directional vector and this is a random point on the line. Okay, so let's see. We have point M. Do we choose a point at random? Is that what they're doing here? Setting the symmetric line of the symmetric equations of the line equal to 0, we see that point P lies on the line. Why is it minus 3, 3 minus 1, 3? But I got, hold on, this is wrong. It's 3 minus 1, 3. Oh, I see. So they're using this as point P. So P M is 1 minus 3, which is a minus 2. 1 minus minus 1, which is 2. And then 3 minus 3, which is 0. And then we have this as V. So the cross product is minus 2, 2, 0 and 4, 2, 1. So the cross product is 2 times 1 is 2 minus with 2 times 0. That's the I part. And then minus 2 times 1 is minus 2 minus 4 times 0 is 0. That's the J part. And then minus 2 times 2 is minus 4. Minus 4 times 2 is 8. That's the K part. So 2, 2 minus 12. 2, 2 and minus 12. Let me see. So if I take this root 4, 4, and 12 square. I have a calculator with me. 4 plus 4, root 152. So I got to root 38. And then for just v, I have 4 times 4 is 16. 4, 1, which is, let me, okay, root 21 doesn't simplify. So P M, or the magnitude of PM, is this over this. Let's see. That's right. Yeah, that's correct. We need to find the distance, right? Given two lines, is there a way we can find them? I'm sure there's a way, but I want to know the equation to find this point. The point which is like the closest to M. Given two lines in the two-dimensional plane, the lines are equal. Given two lines in the two-dimensional plane, the lines are equal. They're parallel but not equal. Or they intersect in a single point. Wait, the lines are equal, or they're parallel but not equal, or they intersect in a single point. I mean, it's possible that the lines are not parallel. Like, one line is coming this way, the other is going that way, and these two will never meet. That's also possible, right? In 3 dimensions, a fourth. Oh, they're talking about 2 dimensions. In 2 dimension, yeah, they will intersect at a single point. In 3 dimensions, a fourth case is possible. If two lines are in space are not parallel but do not intersect, then the lines are said to be skew lines. To classify lines as parallel but not equal, intersecting, or skew, we need to know two things: whether the direction vectors are parallel and whether the lines share a point. So lines share a common point. Yes. And direction vectors are parallel. Then they're equal. Hold on. Can I draw in red? How do I get? So equal is like you share a common point. Pressing Control Z doesn't even work. And that there. Wait, if it's not in the same position. So the directional vectors are equal and they would share a common point. And then it's equal. The direction vectors are parallel, but they don't share a common point. So they're parallel but not equal. So every equal line is also parallel, right? So the direction vectors are not parallel, but they share a common point, so they're intersecting, right? How do I? So non-parallel lines intersecting at a common point. They're intersecting but not equal. And if none of those cases, then the line is Q. For each pair of line, determine whether the lines are equal, parallel, but not equal, skew, or intersecting. So L1 and L2, let's just do it just for the first one. So example 2.48. We have L1 as x is 2s minus 1. Y is s minus 1. And then z is s minus 4. L2, x is t minus 3. Y is 3t plus 8. And then z is 5 minus 2t. This is part A. So uh, x for line 1, I have x, y, z is equal to minus 1, minus 1, minus 4 plus s 2, 1, 1. For line 2, I have minus 3, 8, 5. Minus 3, 8, and 5 plus t. I have 1, 3, minus 2. So it doesn't look like they're parallel, and it doesn't look like they would share a common point. Okay, so it doesn't look like the lines are parallel. So either they're intersecting or it's a skew. So are they intersecting? That's the question. So, let's see. Okay, let's try to make the x equal. So if I have this and this, then I have t minus 2 is 2s. And let's make the y equal. So 3t plus 8 is equal to s minus 1. 3t plus 7 is equal to s. Then let's make the z equal as well. S minus 4 is equal to 5 minus 2t. So minus 2t plus 9 is equal to s. It's very easy to make a mistake here. Let's see, let's add these two. Actually, let's subtract these two. So 3t plus 7. S is equal to minus 2t plus 9. 0 is equal to 3 minus minus 2, so 5. Then 7 minus 9 is minus 2, right? Is that correct? T is equal to 2.5. 0.4. And then S is equal to, if T is 0.4, then 3 times 0.4 plus 7 is 8.2. And let me just make sure it matches on the other one. Yep, 8.2. But does these two value work here? So 2 times 8.2 is 16.4. And then plus 2 is 18.4. It doesn't give the same value of T. So I'm guessing they're not equal then. There is no single point that satisfies the parametric equation for L1 and L2 simultaneously. These lines do not intersect, so they are skew. Okay, let me just try one more for B. Hold on. I'm just opening GeoGebra. I want their I want their 3D calculator. Anyways, so L1 x is minus y, which is C. So x is minus y, which is C. And then L2 is x minus 3 over 2. And then C minus 2. So wait. Okay, so x is equal to t, y is equal to minus t, and then z is equal to t. So x, y, z is 0, 0, 0, t 1 minus 1, 1. And then for the other one, x minus is equal to s, which implies x is 3 minus 2s. Y is equal to s. C is equal to s plus 2. So x, y, c is equal to 3, 0, 2 plus s minus 2, 1, 1. So the directional vectors are not parallel, or maybe they are. Wait. Okay, no, they aren't. Okay, but do they intersect at a common point? So do you have a case where x is equal to actually, let's just substitute t into these values. So t minus 3 over 2 is s, or t minus 3 is 2s, then minus t is s, or t is minus s, and then t is s plus 2. So t minus 2 is s. I think it's easier if I do minus t. So let's just subtract this. So minus t minus t minus minus 2 is 0. T is equal to minus 1. No, t is equal to just 1. Minus 2 plus 2 will give 0. Therefore, s is equal to minus 1. So if we plug in s over here, minus 1 here and plus 1 here, this would make sense. This would make sense. But would this make sense? So 1 over here, 1 minus 3 is minus 2. And then this makes sense. So they do intersect at a common point. That point being, so x is equal to, x is 1, y is minus 1, and c is 1. Right? So for B, yeah, they intersect at 1 minus 1, 1. Sometimes it's hard to tell whether the lines are coming forward or going backward. We know that a line is determined by 2 points. In other words, for any 2 distinct points, there is exactly one line that passes through those points, whether in 2 dimensions or 3. Similarly, given any 3 points that do not all lie on the same line, there is a unique plane that passes through these points. Just as a line is determined by 2 points, a plane is determined by 3. Okay. Imagine a pair of orthogonal vectors that share an initial point. So these two vectors share the point P. Visualize grabbing one of those vectors and twisting it. As you twist, the other vector spins around and sweeps out a plane. Here we describe the concept mathematically. Let n be ABC. So n is this vector. And P x0, y0 be a point. Then the set of all points Q, x, y, z such that PQ is orthogonal to n forms a plane. We say that n is a normal vector or perpendicular to the plane. Remember, the dot product of the orthogonal vectors is 0. This fact generates the vector equation in a plane n dot pq is equal to 0. So n and p are fixed, right? And then q is like any point. So this is the equation of a plane, I'm guessing. Given a point P and a vector n, the set of all points Q satisfying the equation this forms a plane. The equation this is known as the vector equation of a plane. The scalar equation of a plane containing point P with a normal vector n is this. This expression can be expressed as ax plus by plus cz plus d is equal to 0. This form of the equation is sometimes called the general form of the equation. So writing an equation of a plane given 3 points in the plane. Write the equation of a plane containing points P, Q, and R in both standard and general forms. Okay, so write an equation for the plane containing points P, Q, and R. We don't have a dot product. So where do we get the ABC from? Do we do a cross product with P and R? I think that's what we are supposed to do. I might be wrong though. So, example 2.49. Point P is 1, 1, 1, 1 minus 2. Point Q is 0, 2, 1. And point R is minus 1, minus 1, 0. So, P, Q, the vector 0 minus 1 is minus 1. 2 minus 1 is 1. 1 minus minus 2 is 3. P, R, minus 1 minus 1 is minus 2. Minus 1 minus 1 is minus 2 again. 0 minus minus 2 is 2. And then let's just do QR as well. So QR actually so minus 1 minus 0 is minus 1. Minus 1 minus 2 is minus 3. Then 0 minus 1 is minus 1. These are all vectors. Why am I? So vector, 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 vector. So Let's do like a cross product between PR and QR. -2, -2, 2. Let's see. Okay, so this is equal to, so the I part is -2 times -1, just 2, minus it with -3 times 2 is -6. Now minus the j part is -2 times -1, just 2, then -1 times 2. K part -2 times -3 is 6. -1 times -2 is 2. I hope I got this right. So 8, 2 minus -2, 4. You got this. You got this. This is a vector that is perpendicular to the plane. No, hold on. Yeah. It's perpendicular to this. So n, actually we should call this n. So n dot p, and let's call this v. So wait, A, B, C. They want the standard form. This is a vector form. This is the general form. What do they mean by the standard form? Do they mean this? Say A, B, C, x minus x0. So we have C and 1, 1 minus 2. This is x0, y0, c0. Now A, which is 8, x minus 1, plus it with B. Actually, let's just do -4. And then y minus 1 plus 4, z minus z0, so z plus 2 is 0. Is this correct? So let's see. X minus 1, y minus 1. Yeah, I got it right. Okay, so this is example 2.5. Now that we can write an equation for a plane, we can use the equation to find the distance d between a point P and the plane. It is defined as the shortest possible distance from P to a plane to a point on the plane. So we want to find the shortest distance from point P to the plane. Let point R be the point in the plane such that for any point in the plane Q, RP is less than QP. Oh, Q is a point of our choice. So all the other points would be greater than RP. They're basically saying RP is the shortest distance. Uh, the distance between a plane and a point. Suppose a plane with a normal vector n passes through point Q. Okay. The distance d from the plane to a point P not in the plane is given by this. So a distance d. So this is QP. Projection of n QP. So projection of QP onto n. Oh, I see. So this distance. Okay. Find the distance between P and the plane x minus. Wait, hold on. Let me do this. And then 2.51. So P is 312. And the line is x minus 2y plus c. So we have 312 x minus 2y plus c. So hold on. X minus. If we are starting with a line, how do we convert this into these separate forms? Hold on. Uh, I forgot how you convert it into a parametric equation. Okay, so they have n 1 minus 1 and 1. Find the distance between point P and the plane given by x minus 2y plus c is equal to 5. But how do you convert this into into the vector form or the scalar form? And where did they get n is equal to 1 minus 2, 1? Okay, let's just this 1 minus 2, 1. And then do we pick a random point on the plane? Oh no. To find vector QP, we need a point in the plane. Any point would work. Okay, so they said y. So they're using Q as 5, 0, 0. So then PQ is 5 minus 3 is 2, 0 minus 1. They did QP instead. But I still don't understand how they got n from here, like with the coefficient. The coefficient of the plane's equation provide a normal vector. I think they should have gone more in depth with that point. I think it's from this part. So we have this to find. Wait, I want to test one thing. We have x minus 2, x minus 2 plus c equals 5. But instead of 5, what if I type 15? Oh, I see. Or maybe not. Wait. The shape of the plane and the gradient of the plane remains the same if I change this part. Okay, so now I understand. Define vectors QP. So that we have N FPQ, and then to find the projection we need the dot product. 1 times 2 plus it with minus 2 times 1 is 2, and then minus 2, which is just 2, and then the magnitude of N, 1 plus 4 plus 1 root 6, and then lastly get this 2 over root 6. Yeah. Parallel and intersecting planes. We have discussed the various possible relationships between two lines in 2 dimensions and 3 dimensions. When we describe the relationship between two planes in space, we have only two possibilities. The two distinct planes are parallel or they intersect. When two planes are parallel, their normal vectors are parallel. When two planes intersect, the intersection is a line. Finding the line of intersection for two planes. Find parametric and symmetric equations for the line found by the intersections of the plane x, y, z, and then 2x minus 1 plus z is 0. So, how do we do this? Note that the two planes have non-parallel normals. So the planes intersect. Further, the origin satisfies each equation, so we know that the line of intersection passes through the origin. Add the plane equation so we can eliminate one of the variables, in this case y. Okay, this gives us x is equal to minus 2 over 3z. We can substitute this value into the first equation to express y in terms of z. So y is equal to minus 1 over 3z. We now have the first two variables x and y in terms of the third variable z. We now define z in terms of t. To eliminate the fractions, we choose to define the parameter t as t is equal to minus 1 over 3z. Then z is equal to minus 3t. Substituting the parametric representation of z back into the other two equations, we see that the parametric equation for the line of intersection is this. The symmetric equations for the line are x over 2 equals y, which equals z over minus 3. So in order to solve such questions, we have to know at least one point where they intersect, right? In addition to finding the equation of the line of intersection between two planes, we may need to find the angle formed by the intersection of two planes. For example, builders constructing a house need to know the angle where different sections of the roof meet to know whether the roof will look good or drain properly. We can use normal vectors to calculate the angle between two planes. We can do this because the angle between the normal vectors is the same as the angle between the planes. You have 90, 90. So this theta is equal to this theta. Hold on. Yeah, I can imagine this theta being equal to this theta. We may find the measure of the angle theta between two intersecting planes by first finding the cosine of the angle using the following equation. So cos theta is the dot product of these two, the magnitude of these two. We can then use the angle to determine whether the two planes are parallel or orthogonal, or if they intersect at some point, at some other angle. Determine whether each pair of planes is parallel, orthogonal, or neither. If the planes are intersecting but not orthogonal, find the measure of the angle between them. Okay, so let's try this. So we have example 2.53. The first one, and x plus 2y minus c. 2x plus 4y minus 2z. So this is L1, this is L2. Let's say N1 is 1, 2, and minus 1. N2 is 2, 4, negative 2. N2 is just double of N1. So these are parallel, right? So the planes are parallel. Wait, okay. When we find that two planes are parallel, we may need to find the distance between them. To find this distance, we simply select a point in one of the planes. The distance from this point to the other plane is the distance between the planes. Previously, we introduced the formula for calculating the distance in equation 2.19, where q is a point on the plane, p is a point not on the plane, and n is a normal vector that passes through point q. Consider the distance between the point x0, y0, and z0 to the plane this. Let x1, y1, and z1 be any point in the plane. Substituting the formula yields this. We state this result formally in the following theorem. Let P be a point. The distance from P to a plane is given by this. So wait, let me think. So A, x0. What happened to x1, y1, and z1? Or they became k, right? Find the distance between the two parallel planes given by this and this. So 0.100 lies in the first place. The desired distance then is they took d as this. So 2, 1, -1. And where did they get -8? Oh, they calculated k, right? Yeah, I think I understand. Then there are exercises. Okay, I think I will end the stream here. What's the next chapter? Because there's some things I need to study off stream. I'm still getting confused by a few things. Quadratic surfaces. Okay, I think I will leave this for next stream. Anyways, I'll see you guys next time.